All right, so let's start thinking about where molecular geometry really matters in terms of looking at three-dimensional shapes. And so let's look at an example of this with CH3F as our first example. And so our first step is to draw this as it's with its molecular geometry or without it. And let's do it without it first to make it so it's a little easier to draw and to kind of show why it really matters in the future. And so if we look at this, the geometry of this looks, or the Lewis dot structure of this would look like this, right? And so we have 3 hydrogens attached to our carbon and 1 fluorine also attached to it. And so our first thing is to find out whether or not or any of these things or any of these molecules dipoles. Remember, the electronegativity difference has to be between 0.5 and 2.0 in order for it to be polar. And if it's 0.5 or below, then it's nonpolar. And so in this case, we have 2 different types of bonds that exist in this molecule. We have CH bonds and CF bonds. In this case, you have to find the electronegativity difference of both of those. So in this case, you have to find the electronegativity of C and H and C and F. And so in this case, you have to go back to looking at our differences in those values. So C is 2.55, H is 2.20, and F is 3.98. So this is 2.55, this is 2.20, once again 2.55, and this is 3.98. And so once again, we have to figure out the electronegativity differences between these values. So 2.55 minus 2.20, that is equal to 0.35, which means that this is a non-polar bond. Well, in this case, we have 3.98 minus 2.55. That is equal to 1.43. And so this is a polar bond. And so all we have to do now is figure out how to draw this. And so in this case, the CH bonds have no dipoles, but we have a dipole between C and F. And remember, since F has a higher electronegativity value, our dipole will be pointing towards there. And so that is our dipole, where this is our partial negative and our carbon is our partial positive. But let's look at an example of CH2F2. And so our first job is to draw this, and there are 2 ways that you could draw this, right? So if you think about this molecule, if you draw this just as a loose dot structure, there are 2 ways that you could draw this, whether it looks like this or if it looks like this, where the F's are across from each other or next to each other. So across from each other or next to each other. And so once again, we have to draw the dipoles. Thankfully for this case, we already know what the dipoles will look like because we already solved all these things. So in this case, we have a dipole that will look like this, and a dipole that will look like this. And in this case, we'll have a dipole that looks like this, and a dipole that looks like this, where all the arrows are pointing towards our fluorines. And so we have a partial negative here, partial negative here. I guess you could write 2 partial positives here. In this case, we have 2 partial positives in the center, partial negative down here, partial negative down here. And so our job is to figure out, are these polar or nonpolar? Remember, if their vectors or these dipoles cancel each other out, then they are nonpolar. So if vectors cancel each other out, equals nonpolar molecule. What that means is if you find that the midpoint of your 2 vectors, this is an easy way to do this, your midpoint is equal to the same position or the same as the starting point, that means nonpolar. And so let's go through how this would look like with our examples here. And so if we look at this example, if we started from our carbon, right? Because that is where both your tails of your arrows or vectors start off with, is here. One arrow goes up here, and one arrow goes down here. And if you look at the midpoint of this line, so the midpoint between here and here, the midpoint of that vector is still right here. And let's do that in a different color so it's a little bit easier to see. So let's go back to this. The midpoint is right here if the line ends all the way here, or the vector ends here, and the vector ends here, right? And thankfully, that is exactly where we started off with, right? Because we said that our center point, or the ends of our vectors, are both attached to here. And so that is where you start off with. You measure technically the lengths of this in totality, and the midpoint is still in the same place. And so since the end point, or the midpoint, endpoint slash midpoint, is the same as the starting point, this is a quote-unquote nonpolar molecule. While in this case, if we look at this one, our starting point is still at carbon, so let's say it just starts here in between our two vectors. And one vector is pointing down here, and one vector is pointing down here. And if we look at the midpoint of these two vectors, the midpoint would be over here, right? Because one's pointing over here, one's pointing over here. Midpoint of those 2 points is here. And so our vector would kind of look like this as the combination of those two things. And so in this case, this would be our new endpoint. This is our starting point. And since they are not the same, so endpoint is not equal to the starting point, this is a polar molecule. But the problem is with this molecule is that it actually doesn't look like this, right? That these things have three-dimensional shapes, and so we have to actually factor that in terms of figuring out, is this a nonpolar molecule or a polar molecule, right? And because right now, depending on how we draw it, it could look like it's a nonpolar molecule, or it could look like it's a polar molecule. And so let's look at this real fast. So if we draw this based off of what we know, so let's start it off with our drawing, our base drawing of this molecule. Right here, we'll use the nonpolar one for the beginning. What this actually looks like is we have to figure out the molecular geometry of this. In this case, we have 4 bonds and 0 lone pairs attached to our center molecule, right? So this carbon has 1, 2, 3, 4 bonds, and then there's 0 dots associated to it, and so it has 0 lone pairs. And so this has a total of 4 what we call electron pairs. And so in this case, if you have 4 electron pairs with 0 lone pairs, we could actually figure out the molecular geometry of this molecule. And so in this case, if you look at the chart real fast, we go to the 4 electron pairs, and then we go over to 0 lone pairs, and our molecule will actually look like this, or a tetrahedral shape. And so instead of it looking like this right here, it would look like a tetrahedral. And I'm going to make this look a little bit better so that we could actually see where our dipoles are. So this case will look like this, with an F here. And then I'm going to draw the hydrogens over here as a wedge and as a dash, so that it's easier to kind of visualize where these F's and dipoles are. And so once again, remember our dipoles are only drawn as this right here. We have a dipole here, we have a dipole here. And so now what this molecule does, since it's a tetrahedral, right? Our dipoles will never cancel each other out. And so once again, what we have to do is figure out the midpoint of these two vectors. And so we look at this, I'll do this in a different color. If our starting point, once again, is our carbon, our endpoint, our first endpoint is here, our other endpoint is here, and we find the midpoint of those two vectors, it is somewhere around here, right? And so if we drew this real fast, our vector would look like this, where we have a positive over here and a partial negative over here. And so our dipole will kind of look like this overall, because that is the endpoint over here, or the midpoint of our two vectors, and our starting point is still here. And so this makes it a polar molecule because our endpoint is not the same, and our overall molecular dipole is that this side will be a negative charge, and our carbon is still the positive charge. In this case, it's 2 of them, right? Based off of our original drawing, if we drew these right. So let's go back to our original color, or try to get to as close to it as possible, right? This looks like this and this. Oh wait, sorry. Looks like this and this, where this is the 2 partial positive, this is the partial negative, and in this case, this is the partial negative, and then this is the 2 partial positives. But now, the red color in totality is trying to represent the overall molecule dipole, while each of these bonds are shown in blue. And so in this case, we've determined that overall, as a molecule, I'll do it in a different color completely, that this molecule is polar because these two dipoles do not cancel each other out because of their 3-dimensional tetrahedral shape. And so that is how we determine if this molecule is polar or not, based off of their dipoles.